Welcome to another video. In my previous video, I depicted the structure of P-type and N-type semiconductors. This lecture is about construction of PN junction or diode, junction barrier, barrier potential and biasing of diode. The P-type material has an abundance of holes, positively charged carriers, and only few thermally generated electrons. The N region has many free electrons, negatively charged carriers, and only few thermally generated holes. When the P-type and N-type materials are brought into contact, then this is called PN junction, or diode. During this formation of junction, electrons from the N side will diffuse towards the P side, where there is a shortage of electrons. The donor atom left behind positively charged ions, pentavalent ions in N-type region near the junction, since they have lost electrons. In the P-type region, there are atoms that have missing electrons due to the acceptor doping. When holes diffuse from the P side to the N side, the acceptor atoms, which originally accept electrons to create holes, are left behind as negatively charged ions, since they have gained electrons. As the diffusion of electrons and the generation of ions occur near the junction, all the ions are formed close to the junction, creating the junction barrier. And there are no free charge carriers, electrons, or holes left in this region, which is why it is called the depletion region, as all the electrons and holes have been depleted. This depletion region creates an electric field that prevents further movement of charge carriers, generating an equilibrium state inside PN junction. The barrier potential depends upon several factors, including type of material, temperature, and amount of doping. The typical barrier potential at 25 degrees centigrade 0.3 volt for germanium and 0.7 volt for silicon. Now let's discuss diode behavior. P side of diode is called anode and it is denoted by A, and side of diode is called cathode and it is denoted by K. When a diode is connected to a DC power source, this is called diode biasing. Biasing is of two types: forward bias and reverse bias. When positive terminal of the external power supply is connected to the anode, that is positive side of the diode, and the negative terminal is connected to the cathode, that is negative side of the diode, this biasing is called forward biased. To limit the current, a current limiting resistor is added in circuit. Because like charges repel, the negative terminal of the voltage source pushes free electrons, the majority carriers in the N-type region, toward the P-type region in a forward biased diode. When the applied voltage exceeds the barrier potential, typically 0.7 volt V for a silicon diode, it overcomes the junction's built-in electric field. This reduces the barrier and allows electrons to move from the N-type region into the P-type region. These electrons are then attracted to the positive terminal of the voltage source, completing the circuit. As a result, current starts to flow through the diode and the external circuit. When an electron leaves the N-type region, it leaves behind a hole in its place. This hole is quickly filled by another electron from a nearby region, causing the electron to move from the N-type region into the P-type region. In turn, the hole in the P-type region moves towards the N-type region as part of the process. Thus, electrons move from the N region to the P region, and holes move from the P region to the N region. When negative terminal of the external power supply is connected to the anode, that is positive side of the diode, and the positive terminal is connected to the cathode, that is negative side of the diode, this biasing is called reverse biased. Because opposite charges attract, the positive terminal of the DC source pulls free electrons, the majority carriers in the N-type region, away from the junction. Similarly, the negative terminal of the DC source pulls holes, the majority carriers in the P-type region, away from the junction. As electrons and holes move toward their respective terminals, additional positive and negative ions are created at the junction, causing the depletion region to widen and increase the barrier potential. In an ideal diode, no current would flow under reverse bias. However, in real diodes, there is always a very small reverse leakage current. This is due to minority carriers, very few electrons in the p-type region, and very few holes in the n-type region that manage to cross the junction despite the reverse bias. But the current is extremely small. When the reverse voltage applied to a diode exceeds a certain threshold, called the breakdown voltage, the reverse current increases sharply, potentially damaging the diode. In this breakdown region, the high reverse voltage provides enough energy to free electrons, causing them to collide with atoms in the semiconductor material. These collisions break covalent bonds, generating additional free electrons. The newly produced electrons have enough energy to disrupt the depletion region, rather than recombining with holes, leading to a significant increase in current and causing the diode permanently damaged. That's it for today's lecture. I hope you now have a clearer understanding of diode construction and biasing. If you found this video helpful, don't forget to hit the like button and subscribe so you stay updated on future content. Thanks for watching, and I'll see you in the next lecture.